Hello everyone. In this video, I'm going to talk about Monte Carlo simulation. So this is a very powerful computational technique that helps us solve complex problems. And the, the, at heart, we use the principles of randomness to solve this. Uh, so this is a suggested reading. I tried hard to come up with some materials that are less mathy, but unfortunately, I couldn't come across something that might be useful. Typically, Monte Carlo methods, at least the materials that I have come across, are pretty math intensive, and I don't think we need that much math for this course. But this is a link that you can check. Machine Learning Mastery is a website run by a developer. He has a PhD in computer science, and he does a really good job of talking about a lot of machine learning stuff in a very accessible way. One of the things that he talks about is Monte Carlo sampling. So I would strongly encourage you to check out this link. So Monte Carlo simulation is named after the famous Monte Carlo casino in Monaco. There is a very colorful history there, which is a topic for a different conversation. But the idea here is this. So just like gambling relies on chance, this method uses random sampling to tackle problems that would be difficult or even impossible to solve with exact mathematical formulas. So at its core, Monte Carlo simulation is about running many random experiments and analyzing the results to draw meaningful conclusions. Especially valuable when we are dealing with situations that has a lot of uncertainty or many complex variables are involved. So, and this has a wide range of applications: finance, physics, engineering. The Monte Carlo simulation, or rather the elements of this topic, has wide range of usage across many different fields. So let me try and break this down as much as possible. At heart, Monte Carlo simulation involves three steps. Step one, we generate random inputs based on probability distribution. These distributions represent the uncertainty in our variables. For example, if we are modeling stock prices, we might generate random price movements based on historical patterns. The second step involves performing a deterministic computation using these random inputs. This means that we apply our model or a formula to calculate an outcome for each set of these random inputs. And third, we aggregate results from many iterations to form a conclusion. By running thousands or even millions of simulations based on how much computational power you have, you can see that there will be a pattern that will emerge, and then we will calculate summary statistics like averages, ranges, probabilities, etc. So in other words, like, what we're basically doing is that we are trying out many random scenarios and see what is the typical outcome in all of across all of those scenarios. So that is what Monte Carlo is in a nutshell. A very classic example to highlight the value of Monte Carlo is the estimation of pi. Now we all know pi is a constant, which is 3.14, then many digits after that. Uh, you can use Monte Carlo simulation to estimate the value of this constant. And the approach is actually surprisingly simple. So imagine we have a square with sides of length 2. So it's a 2 cross 2 square. And inside that square, we are fitting a circle with radius 1. Okay, so there's a square on the outside, 2 cross 2. And within that square, we are fitting a circle with radius 1. And once we have that, we are throwing random points into that square. Okay. Now, when we are doing that, when we are doing that, two possibilities can happen. Either the point is within the circle, or it's a point which is inside the square but outside of the circle. So pi is essentially what fraction of those points that fall within the circle. And this is the math for that. So if the area of the circle is pi r squared, radius is 1, so the area is pi. The area of the square is 4 because each side is of length 2. So points in circle divided by total points is approximately equal to pi by 4. In other words, pi approximately equals 4 times points in the circle times the total points. So that is the idea. And once we do that, here is a figure where I have taken say about 20 points, and I have thrown all those 20 points inside this whole setup. And these blue dots rather, are the points that are inside the circle, and the red dots are those that are inside the square but not inside the circle. So the number of blue dots divided by the total number of points is approximately equal to pi. And in the code, we will show that as you increase the number of points you throw inside, the accuracy of your estimation increases. At the heart of any Monte Carlo simulation is the generation of random numbers. However, computers can't generate truly random numbers on their own. They are deterministic machines following instructions. Instead, computers use algorithms that generate what we call pseudo-random numbers. These numbers appear random and pass statistical tests for randomness, but they're actually generated by deterministic formulas. The key characteristic of a pseudo-random number is that it looks random, but it is produced by a deterministic process. This means that if you know the starting point, which is the seed, and we use that seed function in the script. So if you know the seed and the algorithm, you can actually reproduce the exact same sequence of random numbers. So that is why setting the seed is critical when you're dealing with random numbers. It lets you produce the exact same results every time you execute that script. So if you run this line of code, I want to generate 5 random numbers between 0 and 1 that follows uniform distribution. I will run this line of code and I will get 5 numbers that satisfy this property. If all these numbers would be between 0 and 1, and they will all be drawn from a uniform distribution. But if I run this code over and over again, I will get 5 different sets of numbers every time. The only way to get the same set of numbers every time is setting the seed just above this and including that line of code in the execution as well. Among other fields, Monte Carlo simulation is extensively used in financial world, where uncertainty is a constant factor. Let me walk you through some common applications. Option pricing. In option pricing, traders use Monte Carlo simulation to produce complex financial derivatives. By simulating thousands of possible price paths that a stock might take, they can estimate the fair value of options that would be impossible to calculate with closed-form solutions. Risk assessment is another application of Monte Carlo. When calculating VAR, financial institutions simulate potential market movements to determine the maximum possible loss with a given confidence interval. For example, they might determine that there's a 95% chance that loss won't exceed 10 million over a one-day period. Portfolio optimization is the third. So instead of relying on simplified assumptions about returns, managers often simulate various market conditions to see how different asset allocations perform across these scenarios. Retirement planning is again another scenario. Rather than assuming a a kind of a fixed 7% annual return on investment, which usually never happens in reality. A planner can run thousands of market simulations based on historical data and probability distribution. And this gives a much more realistic picture of possible outcomes and helps people understand the range of possibilities that they might face in retirement. But all these are different applications, as you can see, but they all share a common theme. They are all replacing simplistic deterministic forecasts with a much richer understanding of a range of possible outcomes, helping decision makers better understand and manage risks. However, this method does come with some limitations. The first and the biggest limitation is computation cost. The more number of simulations you run, the more exponentially expensive the computational cost gets. Now, this cost can come in different forms. The first and the most obvious form of cost is time. You run a model with 10 iterations, it will probably take you less than 2 seconds. But the moment you want to run more and more number of simulations, the time that you will require will start climbing up. So that's a limitation of Monte Carlo simulation. So that is why we have these big processing. We have made so much progress in increasing computation speed by in spending more processors and so on and so forth. But the error also decreases with number of iterations. So that's what we mean by the convergence rate. The convergence rate is what we call it follows this math rule 1 over square root of n, which means that as you increase the number of iterations, which is cap n, your errors will decrease at this rate. The quality of random numbers is another critical factor. Results can be compromised if your random number generator has subtle biases or correlations. Garbage in, garbage out principle says that you are only as good as the model you are using. If your assumptions about distributions or the relationships between the variables are wrong, then even a perfectly executed Monte Carlo simulation will provide misleading results. And distribution selection, which is kind of correlated with garbage in, garbage out. So, long story short, the key thing to keep in mind is that you have to model the problem correctly. Okay? And what I mean by that is that you need to find the right balance between keeping it tractable so that you don't require an infinitely large amount of time to solve the model. But at the same time, the model should not be so simplistic that it gives you results that are pretty much useless. So that is the trade-off, and that is where I think it is more art than science. So next, what we're going to do is we are going to calculate the net present value using some numbers. It's a bare bones structure, but we are going to see how Monte Carlo simulation can better help understand our net present value analysis. And what we are going to do is that, so Monte Carlo simulation will transform this NPV analysis by incorporating the uncertainty that is there in any project related variables. So instead of saying this project will generate an NPV of say 2.5 million, we can make a statement like there's an 80% chance that the NPV will be between 1.5 and 3.8 million. That is a much more nuanced information than simply saying this project will generate an X amount of money. But this approach also acknowledges the reality that we cannot predict the future with certainty. We don't know what's going to happen tomorrow. Variables like market demand, input costs, construction timelines, competitive responses, these are all elements These are all variables that have elements of uncertainty inside them, and that can significantly impact the project success. But by running thousands of simulations with different combinations of these uncertain inputs, we can get a much, much more nuanced understanding of the project's risk return profile. And this allows us to better evaluate whether the potential returns justify the risk involved, and more importantly, the money involved upfront. So let's begin by reviewing the fundamentals of NPV. Uh, so NPV formula is represented by summation t equals 0 to n cf in time t whole divided by 1 plus r raised to the power t, where cf is the cash flow in the period t, r is the discount rate, and n is the number of periods we are looking at. By using discount rate, we are discounting the future cash flows. We are accounting for the time value of money, opportunity cost, and risk. In traditional NPV analysis, financial analysts typically use single point estimates for each variable. For example, they might assume exact values for initial investment, costs, annual revenues, operating expenses, and discount rate. Based on these single estimates, they can calculate one NPV figure. This approach is straightforward, but it has a significant limitation. It completely ignores the inherent uncertainty in these inputs. In reality, future revenues might be higher or lower than expected. Costs might fluctuate. Market conditions can change. Discount rate can change as well. So a single NPV value gives no indication of this uncertainty, potentially leading to poor investment choices. This is exactly where Monte Carlo simulation adds tremendous value, and this is what we will see in the next few slides. So the Monte Carlo approach transforms this NPV analysis by replacing single point estimates with probability distributions that better reflect real world uncertainty. Instead of using a single value for each input, we define uh, we define probability distributions that capture the range of possible values and their likelihoods. For example, there can be uncertainty in the initial investment cost. Suppose you're planning to spend X million dollars, but there's no guarantee that you will be able to get that enough funding as an initial cost. Your annual stream of revenues and operating costs can fluctuate. There can be uncertainty with how long the project is supposed to run. Sometimes projects can overrun or they can end sooner than expected. There can be discount rates, there can be inflation that affects uh, operating costs and revenue. So there are many, many, many different ways things can not go as you have planned. So what we need to do is we need to, instead of setting values specifically to get a single NPV, we need to pick a distribution that is appropriate for each variable. And that can be based on historical data. So suppose you know a certain variable reasonable like follows a certain distribution with uh, reasonable amount of justification, you can pick that. Or you are an expert in that domain and you know something, you can use any of these sources of information. There are different that's why we have so many different kinds of probability distributions. It's there for us to use as and when needed. You can also go one step further and also account for correlation between variables. So it's not just that these variables are completely independent of each other. There can be correlation among them as well. So Monte Carlo simulation also allows for you to account for these correlations as well. So there are so many different things that you can do. We are gonna avoid much of those complications and we're gonna stick to a relatively bare bones structure when we show the outputs for that. So what we will do is we will create thousands of scenarios. Okay, once we have set the probability distributions of each of these variables, we are going to create a large number of possible scenarios using those numbers as the initial starting point. Now, there is no hard and fast rule about how many scenarios you need to create. The rule of thumb is the more the merrier, but again, then you run into the risk of computational challenges. Typically, any number between 1,000 and 10,000 is pretty standard. So that's that. And for each of these scenarios, we are going to calculate what the NPV is in that scenario. So suppose I have scenario one uh, where suppose the initial expenses is at a certain level, my annual return is at a certain level, my cost of operation is at a certain level, and I have some numbers plugged in as a starting point. What I'm going to do is find out what would be the NPV when the numbers are that, and I'm going to store it somewhere. Then I'm going to redo this whole exercise, but the only thing I'm going to change is the initial starting point. I'm going to randomize that initial starting point and then let my function take over and generate the NPV for me. So for each of these scenarios, be it 10, be it 1,000 or 10,000, I will get an NPV, and that will be my distribution of NPV. So instead of working with a single number, I will work with a distribution that has a lot more information. And from there, I can calculate a lot of important stuff. For example, I can calculate what is the probability that the NPV will be positive. I can calculate the expected NPV, that is the average across all simulations. I can calculate confidence intervals. I can calculate which variables most impact NPV. We are not, we are going to skip the last part, but we are going to focus more on the first three. So suppose I have a new manufacturing plant. This is an example. So I have a plant that I want to set up, and the project details are as follows. So I'm expecting the lifespan of this project to be 10 years. I'm expecting an initial investment of $5 million. But note this. So I'm expecting 5 million, but I'm also expecting that it comes with with some some element of certain uncertainty. So there's a 20% chance this is going to be more than or less than 5%. My annual revenue I'm expecting to be 2 million with a margin of 30%. My annual cost is going to be 1.2 million with a margin of 25%, and my discount rate is 10% with a margin of 2. Uh, if you calculate it as a single point NPV, suppose you get 3.26 million. Okay, this is just a number. Do not go plugging in the number and using the formula. Just think of this as what if you get this number. So suppose you get the single point estimate as 3.26 million. The first question that should pop up in your head is, how reliable is this estimate given the uncertainties? Note that the uncertainties are over here. So plus minus 20%, plus minus 30%, plus minus 25%. These are your uncertainties. So given these uncertainties exist, how reliable is this 3.26 million? That is the question. And that is why we need a Monte Carlo simulation. So suppose we do the simulation and we do it for 10,000 times. So 10,000 times we are creating scenarios and looking at the NPV, and we see that the expected NPV is 3.1 million. But but we also have some other information as well, which are very useful. We know that the NPV will range from negative 4.2 to 11.5. So as compared to the 3.26, there is at least some chance that we will lose money on this project, and there is at least some chance that we will make way lot more money. The probability of positive NPV is 82%. So there's an 82% chance that the NPV will be greater than 0. Probability that the NPV will be greater than 5 million is 35%. So 5 million was my initial investment. So the probability that my NPV will exceed my initial expenses will be is 35%. And my 90% confidence interval is between 0.5 million to 7.2 million. So if I keep doing this exercise over and over again, the probability that the number will lie between these numbers is 90%. Now, if you compare this with the traditional NPV estimate, this is a far more nuanced view of the project risk. Okay, now you have a lot more information that you can use to make this decision about whether or not you should open this new manufacturing plant. And this is the distribution of that NPV. As you can see, the traditional NPV is here, but we also have these all other values that we can potentially see if the situation is in a specific way. So to summarize, Monte Carlo gives us a much better assessment of risk because it explicitly accounts for uncertainty in our decision making. We can also do sensitivity analysis. We can identify which variables to focus on, which of these variables that we're working with, which of these variables, how sensitive they are. We can do that. And we can also create multiple what if scenarios systematically. So if we tweak the numbers, okay, if instead of 5 million, if I do 10 million or 2 million, what would the scenario look like? We can do that as well. So in R, this is the broad step. In a separate video where I've gone through the R script, I talk a lot more, but this is the general structure of a Monte Carlo. We begin by loading the necessary packages. We need tidyverse for data manipulation. We need MC2D for some distributions of probability, not all. We need ggplot2 for creating graphs, and we need the mass package for dealing with multivariate random number generations. Not all of them are super essential for the barebone Monte Carlo that we will do. For that, we only need ggplot2 and another extra package called grid extra. So we begin by defining the NPV function. Since NPV is at the heart of our analysis, we need to write a function that calculates NPV for us based on the information that we provide. So we create a function that takes in the initial investment, cash flows, discount rate, and number of periods, and we will write a function. So what this means is that if I take this function and plug in these numbers, then it will spit out a single number that will be the NPV based on those numbers, or those parameters. We have a whole list of options to choose from as far as probabilities are concerned. Some of the typical common feature, normal distribution is one of the most commonly used distribution. They have their own strengths and weaknesses. So this is generally good for revenues, costs with symmetric uncertainty. We also have a couple of new distributions that we haven't talked much, but it's not super important, but definitely useful to keep in mind. Triangular distribution is good for variables where you have a minimum, the most likely, and the max value. So if you have a variable which has some minimum value, some max values that can happen, and some values that are most likely to happen, A triangular distribution does a good job of capturing that variable. We also have a PERT distribution, which is similar to triangular but with smoother tails. We have log normal distributions. These are good for variables like prices, asset values, costs that cannot be negative. We have beta distribution, which is good for proportions, efficiency rates, and utilization percentages. So your choice of probability distribution depends critically on what variable you're working with. Okay? If you don't select the right distribution, even if you are doing the right exercise, you will get results that are completely off. So you need to be careful about making these selections. Discrete distributions is good for categorical scenarios or discrete events. So if I want to plug in a market scenario where I'm only defining market scenario as three possible outcomes, low, medium, and high, then what I'm going to do is I'm going to create a vector with low, medium, and high and use the sample function to randomly pick any one of them from there. I can do it. I can assign equal probability. I can also assign probability that are more realistic, maybe like medium market scenario is probably most likely as compared to low or high. So I'm assigning 50% chance to medium, 20% chance to low, 30% chance to high, and you can tweak these numbers. Okay, this is just for exposition. In the real world, these variables that we're going to work with, they are not independent. They are often correlated with each other. So we can also define a correlation structure, and to do that, we use the MVR norm function from the mass package. There, this code so these codes create a correlation matrix. So first I define the correlation matrix, which is, so it's going to be 1.7.71, and then I'm going to generate a data which follows a multivariate normal distribution, 1,000 observations. The means are 100,000 and 60,000, and the correlations is, instead of defining specific standard deviations, I'm going to plug in the correlation matrix. Okay, so suppose I am defining, I'm generating revenue and cost in that way, and I believe revenue, and it's fair to believe that revenue and cost are correlated. This is one way of